thought it was already going. There you go.
I did ask you.
Sorry. All right. Do you want to go back from the top? Sorry.
Yeah. All right. We'll start again. So yeah, everybody who's here already knows we're learning about natural language processing, but people on the internet now you know. That's what we're doing today. So, yep. Who am I? I'm Yaku. I work at Notive. So at Notive, I head up the machine learning team. We basically focused on audio processing and natural language processing. The reason is we're building a bot for joining your meetings, and once it's joined your meetings, it basically takes action items and notes for you. I'll show you a couple of examples in a second. And yeah, we basically build all the NLP ourselves to discover the interesting things and present you additional context and things of interesting. We're also hiring for natural language processing. So if anyone finds the stuff I talk about today interesting, feel free to reach out, including internet people. We do support remote work, so feel free to reach out to me if you're interested. So a little bit about what we do and what I do in my day job. Here's an example of an action item extracted from Notive. So we'll do that tomorrow is the action item. Obviously, just the statement, we'll do that tomorrow, is not that useful. So you need to understand a little bit of the context. So we've had a sentence classification model similar to the one you'll be learning today, which is predicting is that an action or not an action, right? Or in the examples we're looking at here for IMDb is that a positive review or a negative review? And so once we've classified these actions, we need to go a little bit further and add the context. So an example here of understanding context is, we're going to set some cycle kickoffs, set some objectives. So that's what that is referring to. And some additional context. So we're looking at tickets and we're setting some objectives for the cycle. So these are the sorts of problems we're looking to solve. The other interesting avenue is taking a big portion of text and breaking that down into a shorter summary. So just some of the other things we're working on. Okay, here's like the stuff I'm going to talk about today.
Yeah, okay, before we move on, I'm curious. Summarization, what's the typical approach to doing that?
Yeah, so there's two key approaches. One is called extractive summarization, which is, again, like a classification problem. So you're basically going through the text and for each sentence saying whether or not this should be part of the summary. And that can work well when you want to be like factually correct. And we tend to, for the most part, focus on that sort of summarization. The other one is called abstractive summarization, and it'll often center around a sequence-to-sequence model that's taking the input, and it builds an encoding of the input, which will be like a vector, and then you decode that decoding into a summarized, rewritten version of the what was written there. Yep.
Which one, or is there in the area of creating indexes for text? Like when you have a big book in a encyclopedia, at the end of the book you have an index that picks out key terms and explains them.
Yeah, so if you have a look here, that's exactly what we've done for these meetings. Well, maybe not explaining them. So what we've done is built more of an index into the topics that are being discussed in the different sections of the meeting. And that's alluded to here. Talking about what you're discussing there. I don't know that I've seen anyone do an index on explaining, but I definitely think something like that is plausible and should be possible to do with a machine learning based algorithm. Just like a simple approach off the top of my head would be to have a language model and give it a prompt, something like, when I use this word in a sentence, and then let it finish that off and see if you can get that to give a description of what that word means. So you're just using a language model like a 5-year-old could be like one basic approach to get something like that to work.
That would not address the cherry picking of which terms should go into.
Yeah, so you probably need, like in that approach, like a multi-stage pipeline of, and then that really depends on like what the person reading the in-text cares about. So you need to have a domain understanding of what you're trying to build a problem for in order to solve something like that. And then, you might use a non-deep learning approach to maybe use TF-IDF or something to come up with a set of candidate words. And then from there, you could present the candidate words to the person and let them choose these 5 are what I'm interested in, or it really depends on what sort of product you're trying to set up. So, but yeah, that's at the end of the day, when you're doing AI as a product, your job is to work out how to use my hammer to solve real user problems, right? So there's no one right answer. It's about similar to when you're in high school and they start giving you problems where it's a whole bunch of words and you have to turn that into math. That's the same problem here. You have like a whole bunch of objectives and you have to try and work out what is the math that solves that problem. So yeah, it really depends on your requirements and stuff like that. Was there any other questions? Everyone's good? Cool. Yeah, I'm going to recap some content. Then we're going to talk about Sesame Street. Then what to do when things go wrong in NLP, and they do go wrong. A little bit on how to make your models better. That's actually the paper review. And then we'll dig into some code examples and other interesting things like that. So what is the natural language pipeline that Jeremy has presented to you? So it consists of a tokenizer, numericalization, and batching, embedding, the model, which for those who didn't go through the notebooks, it's basically the same as the linear layers you've seen before, but with a for loop inside of it, and then some extra tricks to make it perform better. And then there's a classification head. So everything up to here basically gives you an encoding, which you can use for a number of tasks. As I mentioned earlier, the sequence-to-sequence model will then take that encoding and put a decoder head on the end of it and produce text output again by doing prediction. Jeremy teaches, or he used to teach that in part 2 of the course. I don't know if he still does, but they have an NLP specific course for people who are interested. I have that linked later in the slides, where they do go through a lot of other things you can do, not just classification with natural language processing. Okay, so this is like tokenization, right? So why do we need to do tokenization? Well, if we think about it, what is writing? It's a collection of symbols that we decided should be put next to each other. And basically, here's an example where we've put the $sign next to a 1. So can anyone think of a reason why the $sign and the 1 need to be split from each other? Why is it important for that to happen? Yeah.
They've got 2 different meanings.
That's one meaning, one important reason. But exactly, yeah. So when you have these tokens, they're going to go into your vocabulary. So when you have $1 or $2, you don't want to have, let's say you have dollar numbers from 1 to 60,000 somewhere in your dictionary. You don't want to have a vocabulary item for $1 and $2 and $3 and build an embedding for what does $5 mean. It's just the same as the vocabulary for dollar and the vocabulary for the number added together. So instead of having a combination for all of these, we can separate them out and then build embeddings. So that's one of the key reasons why we want to do this. It's building the list of candidates that are going to go into our vocabulary. The other thing that Jeremy adds in Fast AI that's pretty nice is these additional special tokens. So Obviously, the beginning of sentence token, you'll see that whether you're using Hugging Face or any other machine learning library, but less often do you see these things like xxrep3, which indicates that there was 3 repetitions of a W, and the xxmaj, which indicates that the next one was an uppercase letter. So these serve a similar purpose to the splitting that we were talking up here. It's basically reducing the space of things that the model needs to learn. So it just needs to learn what uppercasing a word means. So this uppercase token always precedes something that's going to be uppercase. So it doesn't need to learn what fast with a lowercase and fast with an uppercase means. It just needs to know that the uppercaser came before fast. So that's why that sort of stuff's useful. Okay, so numericalization, it's basically take your set of tokens and apply the vocab to them. So get some numbers out. These are going to be the indices into your embedding matrices. So you guys learned about embedding matrices earlier. This is basically the same stuff. So these are going to give you where in your embedding matrix do you need to look up the vector for this particular word. Which brings us to batching. The batching for the language model is a bit special and different from the batching you've seen in other tasks. So here we have an example which is 90 tokens, and in this example the full data set is 90 tokens. When you have a real example, the full data set will be many millions of tokens typically. So you're not going to be able to fit everything in one batch like we've seen here in the first example. So what they do instead is you break the data into what are called mini streams. Okay, so for a batch size of 6, we have 6 mini streams. Yep, each of sequence length 15. Right? So if we had many millions, we would have many millions divided by 6 sequence length for each mini stream. So we would still have 6 mini streams, but they would go on for many millions divided by 6. So what happens then if we use a shorter sequence length, we use 5 instead of 16, is the first batch becomes this window of the full data. So it, in this chapter basically is the first row of the first batch. The second row of the first batch is movie reviews we studied in right? So it's not actually related to the row above it. But if you go then to the second batch, the first row is immediately following the first row in the first batch. So we're not doing random shuffling or anything like that. We're maintaining the ordering from batch to batch. And as we go, the batches are going to slide over this sort of pseudo batch. You can pretend there's like you've taken all of the data and broken that into batch size, one thing that's like batch size 6, but the full length of the data, and then your batches are without overlap sliding over that data. So this is something that's very confusing for people, and has anyone got any questions? Or yes?
So if you have these batches, do you maintain the context that 2 batches actually span context of a sentence or a phrase, and that multiple batches actually are connected, or do you treat them as isolated, siloed kind of blocks of business?
Yeah, so the context. Okay, so the question was around, does the context get kept, or are we treating these as essentially independent? And the answer is yes, the context is kept, and because of the way the RNN works, when it sees the next batch, it remembers what it saw in the last batch. It's got like a basically like an encoding. So maybe a bit later when we'll see some of the sort of actual code. I think it's like the hidden to hidden layer. But anyway, there is a matrix in there that keeps that context from batch to batch. So that is the reason why we set it up in this way, so that you can use the fact that this preceded it when you're doing your predictions for this section. Was there another question? No?
You have the batches horizontally, so you would have six blocks and three each instead of columns.
6 blocks with 3 rows each.
So 3 blocks would be one batch.
So you want to reshape the batches.
So doing rows.
Doing rows instead of columns.
Yeah. And with the rows, you want to do that one, and then it'll work as long as the next time the model comes through, it's looking at the data that immediately follows the data that came before it. So you would have to probably change the way it's sort of feeding the batches into the model internally. Yeah, that's my understanding, but without looking at the code, can't actually give you the clearest answer on that one.
So it constructs these batches in the right order, so then it goes through the data.
Yeah.
Do you remove filler words like while, when, to, or do they provide context?
Yeah, in natural in deep learning models, we don't remove the filler words typically. Yeah, they do provide additional context, and I think it was Jeremy, but I've seen a presentation somewhere where people looked at like what performance you get with and without, and you get better performance if you leave them in there. Okay, and so as we discussed, the next part is that the words go through the embedding, which is basically converting each of these words into their numerical representation. So that's going to be a list of numbers. I believe we use 400 dimensional numbers in this data. So yeah, it basically gives you the ability to have a representation that can be updated through the backprop process, and yeah, just work with the data in a way that is comfortable for a computer, which, like, no doubt we have some sort of similar representation in our own heads of, like, I don't think numbers are represented with letters in your neurons. So there's some pattern of activations which is similar to, not exactly similar, but conceptually similar to this happening with when we think of when we think of words ourselves. Alrighty. So this is just a bit of a overview of what the actual model looks like, and the main takeaway was that the model works by taking a word in, applying activations to it, putting that through a linear layer, and then it puts the next word through an activation and adds that to the previous context, and then puts that through another linear layer. Then it puts the third word through a piece of context and adds that to that next hidden layer. So this piece of information from here has flowed all the way through the network. So we're maintaining the context of this information. This actually gets wrapped up into a for loop in the code, so it doesn't get shown in this exact way. But this is the basic essence of what the difference between a recurrent neural network and just a normal linear layer. And then because we end up with, when we do this for long sequences, this issue of exploding and disappearing gradients, because it involves repeated multiplications. And so if our activations are at all above or below 1, we end up multiplying by something that's a bit above 1 over and over and over again, and so that runs off to infinity, or we multiply by something a bit below 1 over and over and over again, so that runs off to 0. Schmidt-Huber and some of his friends came up with this gate system that allows the model to still maintain the context over long periods, but avoids these disappearing and exploding gradients. So I'm not going to dig into that because it'll take a long time. And no, just this, dig deeper into how the LSTM actually works, but it also is I see what you did there. But what I would recommend is, if you haven't already, go and watch the second part of the lecture Jeremy gives. It's Notebook 12. He goes into quite a lot of detail about this, and in that you find he does say in there somewhere, okay, this is the part where it maintains the state from batch to batch. So he does explain it in there. All right, so now we're up to everyone's favorite furry friends, the Sesame Street. And basically transformers, all you need to know is Sesame Street. It started off with a paper, attention is all you need. So for those who don't know, transformers are an alternative model to recurrent neural networks for working with sequence data, and natural language is sequence data. So that's the other thing to remember, is that all of the stuff that we're learning here will work for generally any sequence data. It's not restricted to words. So we turn something into an embedding. If you can turn something into a vector type representation and it's happening over and over again, these types of models are going to be applicable. So if you've ever heard of BERT or LBERT or GPT, I think if you haven't heard about GPT-3, you probably don't care about natural language processing. Everyone's heard about it. So they're good, they do their job, but they can be large and expensive to train, and they're not always needed. So you can get good results faster with some of the things we're going to look at here. You won't always get as good of a result, but you can still get very competitive results with some of the things Jeremy's presented. So what I wanted to do, let me just have a look at how much time there is. 6:30, yeah. So while I was preparing these slides, somebody actually put onto a Twitter post about this multilingual language processing, and Jeremy put in a reply saying, they cite multifit and LSTM, but then suggest that transformers are only used in the space. I still hear a lot of folks in low resource learning space that get better results with multi-fit or ULM fit style approaches. So it's just interesting that the whole community has sort of shifted towards these transformer models, even though you can still get good results with RNNs. And I wanted to read the abstract of this paper. I'll just read a little bit of it for some light entertainment, because it's very, very funny. And if I don't read all of it, you should definitely go and read it afterwards. It says, the leading approaches in natural language in language modeling are all obsessed with the TV shows of my youth, namely Transformers and Sesame Streets. Transformers this, Transformers that, and all over here with the bonfire worth of GPU, TPU, neuromorphic wafer scale silicon. We opt for the lazy path of an old proven technique with the fancy crypto-inspired name, the single-headed attention RNN. The author's lone goal is to show that the entire field might have evolved in a different direction if we had instead been obsessed with a slightly different acronym, slightly different results. We take a previously strong language model based on a boring LSTM within a stone's throw of the state-of-the-art byte-level language model results on NWiki 8. The work has undergone no extensive hyperparameter optimization and lived entirely on a commodity desktop machine made with the which made the author's studio apartment far too warm in the San Francisco summer. The final results are achievable in less than 24 hours on a single GPU, as the author is impatient. The attention mechanism is also readily extended for large contexts with minimal computation. Take that, Sesame Street. So, yeah, I quite enjoyed that one. So, even though transformers isn't necessarily all you need, they do a lot of cool things. And for those who don't know, AlphaFold 2 was recently released by DeepMind, and it does make extensive use of the transformers models. AlphaFold is this basically solved a 50-year long-standing problem in computer science of how do you take a sequence of nucleotides and work out what protein it will fold out of those, and DeepMind has solved that problem, and it's going to have potential to make some very big changes in how we make medicines and things like that. So I would recommend learning about these. There's 3 great resources here, which I wish I had when I first started learning about transformers. So definitely recommend them. And this NLP video 18 is the video from Rachel, which is Jeremy's wife, that is the full NLP course. So if you're interested in NLP, check that one out. A couple of examples of how things can go wrong. So this is looking at what's called disfluency. So when is Easter this year? When is Lent? Easter this year. Things like that. They're basically looking at this BERT question answering algorithm on the squad data set. So they find that when you add this sort of disfluencies without doing any special tricks or training, you get a 19% drop in the F1 score. So just be aware that if you find something that is a paper and it's awesome on some perfectly written text, that it might not apply as well to your transcription of somebody talking. So noise is very much a thing in natural language processing, depending on the source of your transcript. So you might all have heard that sentiment classification is basically solved because we can get 90+ percentages accuracy on our classification problem. So here's a nice example of when it cannot be solved. It says, thank you for sending my baggage to Hyde and flying me to Kolkata at the same time. Brilliant service. And they're glad to hear it. Are you serious? Be careful around the edge cases. So they're less impactful than in self-driving cars, but they can be embarrassing nonetheless. This is the end of the presentation, getting towards the end. There's this paper that Jeremy links to in the presentation where they take the 25,000 examples that we used and reduce that down to 20. And they say, can we get the same results with just 20 examples as 25,000? And they basically end up beating the results that they got with 25,000 using just 20 through a number of tricks. And if there's enough time, what I thought we could do is everybody could have a bit of a read through this paper for 5 minutes or so. And then I can ask a few questions about it and keep presenting a little bit. Is that something you guys be interested in? What do you reckon? Everyone excited to read a paper? Yeah. All right. So I'll post this link in the Discord. Whoops, didn't copy the link. If you just Google for that 1904, whatever, it'll come up. All right, that's probably enough time, mainly because I'm getting bored. So, I hope that you guys at least made it to this slide, because this is mainly the key essential part of this talk, and I can show it over here. So what are the tricks that they're using? So the trick is a data augmentation trick. The main important one from a natural language perspective is this thing called back translation. So back translation is the concept of taking an input text, you project it into a foreign language, and then put it back into your native language. I'm sure you guys have played this trick, this game with Google Translate before, but it turns out it's actually very useful for making more examples for your natural language processing models. So just reading these ones, given the low budget and production limitation, the movie was very good. And then it's come back with, since it was highly limited in terms of budget, the production restrictions, and the film was cheerful. So it's basically paraphrased with like some weirdness, but what was said over there. This last one is kind of interesting. Due to the small dollar amount and production limitations, the Aoist film is very beautiful. It starts to become a bit of a stretch whether it's a paraphrase, but it's in the right ballpark. Anyway, so what...
Industry-specific examples of that. I'm thinking like medical industries or something like that, where one doctor would say one thing but could be interpreted in a number of different ways.
Yeah, for sure. And like the back translation is one way of doing it, but the main point is you need an easy way of producing paraphrases of your input. So the problem with getting doctors to do it by hand is that it's a lot of effort. So the trick here is that you're trying to use something that you've got a lot of... We're trying to exploit the fact that we've got a lot of labeled data for translation to make our other models do a better job, right? By basically providing it with a broader context. And therefore you're saying it like, in this context, that context, and that context, we want the same label from you. So, you know, maybe a good idea in that one would be if you had like a model that was specifically good at medical translation. So, you know, translating medical documents into other languages where you got to be very precise, make sure you're not using the wrong words and stuff. That might be a good candidate for using in a scenario like this. So just an idea. Okay, so coming back to how do they actually do it? So this side here on the left, does this look familiar to everyone? Who wants to have a stab at explaining this picture? Anyone? No? Okay.
It's the normal training that we do.
That's exactly right. This is...
Look at the labels and we predict with model and compare them.
Exactly, and we have some loss. So we predict, this is our input, this is our label. We put the input through the model, and we use the loss function to compare. So this on the left here is nothing more than everything that you've already seen. Then we have this unsupervised consistency loss on the right here. So they take in some more unlabeled inputs, X. They apply the augmentation, in this case we're looking at back translation, to that X. They put both of them through the model and apply the unsupervised consistency loss, which is, and if you read the paper, you'll see that they're basically just taking the cross entropy loss between the distribution when you put the augmented X and the non-augmented X through the model. So it's basically saying we want you to make the same predictions for the augmented version and the non-augmented version of the unlabeled data. And the end result is you end up with a more robust model. So you're instructing it that it's even without labels, for these particular examples, just produce the same output. There's some little tricks they do. Confidence-based masking, they basically define this beta, and the beta just says don't use the gradients if the loss is less than beta. So sorry, if your confidence is less than beta. So if your most, like let's say you're doing a prediction of, is it a positive review or a negative review? If you're not more than 0.8 confident, then when you're doing this one, for instance, you take the unlabeled data and you predict whatever you're predicting and you're not confident about the answer, then don't use that data. And then this other one they talk about, which is basically just saying that you can actually do this same technique with data that's outside of your data set. So you can take some data from a totally different unlabeled data source that you don't have any supervised labels for, and you can still apply this technique to it. And you just got to do the same basic beta, only apply it if your model is confident on that data. So
are there any examples or papers of people using this to help models generalize better to OOD datasets?
Quite possibly, but none that I've seen so far. So one of the concepts that I wanted to demonstrate is that this paper that gets an amazing result is actually basically boils down to this, which is all concepts you guys already understand. But what they put there is this, which looks scary, at least to me. I don't know. Maybe it's just me that's scared of squiggly Greek symbols. But it's actually not that complicated. What this is saying is take your loss function, which is just your softmax, look for the one that had the highest value, and if that probability is greater than 0.8, then use the cross entropy. Otherwise, you set the value of that loss to 0. So it's basically just applying this confidence-based masking, which is a very simple concept. Just doing a test. This is basically an if statement in funky-looking math terms. So this indicator function is going to output either a 0 or a 1, depending on the condition that's inside of it. So if the maximum probability is greater than beta, it's a 1, otherwise it's a 0. So that's pretty simple. This one is saying you take the cross entropy loss between the probability predicted from just your unlabeled input and compared to the probability predicted from your augmented unlabeled input, and they add a little bit of fanciness to their softmax, this sharpening by tau, which is basically dividing by a number in the softmax. So we've already seen in this course how to implement the softmax function and cross entropy, and the indicators easy. Dividing by the size of the batch is easy. So everything here looks scary, but it's actually very simple. So in the second part of the course, Jeremy will teach you more about digging into papers, but I would encourage you to not necessarily wait too long, because quite often you can get amazing results with things that are quite simple. So does anyone have any questions about this paper? Yep.
This is not a question or a comment. I'm a little bit amazed how you can put an if statement in there, still gradient is well behaved, and you can like train it.
Yeah, exactly.
I was on the assumption that this kind of thing might make the gradients very badly behaving.
Yeah, that because it's like a discontinuity, basically, right? Yeah. And but it works. Any other comments or questions? Well, yeah, I think you guys should be excited about this because it's pretty awesome. It's not very often that you get to see something where 20 examples beats 25,000 examples. So deep learning typically is the space of very large data sets. And let me tell you, I'd rather label 20 examples. Anyone who's ever done labeling does not want to label 25,000 examples. Yeah.
You mentioned before around summarization. Is that a form of, I guess, supervised learning where you may say, here's 3 or 4 articles and here's a summary for those? So if your job was to produce a summary based on a series of, I guess, documents, how would you train something to be able to create that summarization?
So it's basically, like I said before, there's 2 approaches. one is called extractive summarization, which is basically taking candidate pieces of the input text and saying, okay, keep this, but get rid of all the rest of it. So these sentences together form the essence of what was written there, and that's called extractive summarization. The other one is called abstractive summarization, where you're trying to rewrite what was written there into something that summarizes it. And the approach there most commonly is to use something called a sequence-to-sequence model. And yeah, you would need many more than 3 examples of what a summary looks like for that particular thing. And most often what you'll do is start off with something like the CNN summarization data set and fine-tune from something like that. Okay, well that's all I had for the lecture notes.
One question about so some of these new techniques, particularly semi-supervised stuff, there's obviously been a number of papers come out in the last 6 to 12 months. If someone was just getting started or catching up on some of this, are there any libraries or toolkits or methods that you can basically just import a library and quite easily use some of these techniques versus having, like, some of these obviously aren't readily available?
Yeah.
In an easy way?
I mean, like, they did release the code for this, so quite often they do release the code along with it. But one of the things you sometimes find is it's almost easier to re-implement it yourself, because sometimes the code's not set up in a way to handle the data that you want, and then in order to get it to work, you end up sometimes having to understand all of their code, and if it's not nicely written, it can end up being more work than just understanding this simple diagram and then using their code as a reference. In terms of libraries for semi-supervised learning, I'm not that aware of any, because they're typically more small modifications to existing models. So you might have like a normal PyTorch model and then use a different loss function, or add an additional loss function, as we've seen in this example. So I don't think people often rewrite a whole new library for something like that. Yeah, that would be my main comment, is like, it's implementing stuff like this is often not too challenging. So people just augment their existing model. So what I would recommend in that case is just having a look at the source of how somebody else has done it and making those adjustments yourself.
I guess too, if you're having to fetch translations, you'll need keys for that as well. I'm not sure if you can do it at scale that easily.
Oh, they provide a model for doing the back translation.
Okay, cool.
And also with the Hugging Face, I did start actually implementing this as a notebook, but I didn't get time to finish it, so I might turn it into a blog post instead, running through how to do this. But yeah, with Hugging Face you can do the back translation, and then Google, who are the ones who wrote this paper, also provide, I think it's called Tensor to Tensor, which is a back translate, well, it's a translation sort of library, but they give you like, okay, these are the commands to pass in. So one of the things that you do need to change is to use, I think it's a high temperature. So what it does is it produces a lot of variance in your outputs. So if you have too low of a temperature, each time you run it, you'll get the same output, which obviously doesn't help for back translation. So you want it to be not too high that it's producing crazy stuff that's totally unrelated to what's here, but high enough that you're getting, a good amount of paraphrases for a given input. Yep. Is there anything else? Yep.
I'm just curious in general. I kind of miss the use of grammar elements and classifying that verbs are nouns. Like the grammar structure of the sentence. I miss that. Isn't that a lot of information that we help me predict certain sequences of words if I knew the context, the contextual grammar of what I'm trying to repeat?
Yeah, so the idea with end-to-end models is the same way that we don't have our vision model and give it a specific filter for telling edges. It learns that filter for edges itself, and in the same way the language model is learning the grammatical rules of your language on its own, so you don't have to hard code those in. Where grammatical codes can be useful as an additional filtering step afterwards. So if you have an action item, for instance, which has a very specific grammatical pattern, you can do an additional filtering step where you get all those grammatical rules. So Spacey, which is the library that does the tokenization, also has deep learning models built into it for producing all the punctuation, and it builds a dependency graph of how all the words relate to each other. And you can use those tools, and we often do use those tools as secondary information. So these semantic segmentations and tokenization, topic techniques, that you can't see it very well, it's a bit blurry, but this is basically a list of topics for that part of the call. We don't actually use deep learning models for that. We use more these old school NLP models that you're talking about there, because there's no competitive, or at least not that I'm aware of, easy to use, good deep learning solution to these problems. So people have tried, but they're often not as good as the simpler solutions. And yeah, that would be my comment on that. Anything else? No? Okay. So if people want, you can, I posted the code exercises there. Go and have a look at it if you haven't already, and I'll take a little break, and then we can come back to have a look at the code exercises.
tested to see if it could convert that bit. Or push it into a, are you modifying it on a branch or like master and then whatever? It's a branch, like just create a, yeah. Oh, that's. But that's just type in the just commit it and push it. You're going to go. Okay, yeah, you do need to do that. Right, because on mine, I'm always connecting it. Okay, now it's a bit repo, so now you need to push it into the center of the
Yeah, and I can, then it's actually
yeah, that's a new project. Yeah, there's a thing where you add a and I'm sitting here going wrong if it doesn't work. But then I'm thinking, oh, having things like partway through is not fun. Oh, there we go.
Well, I don't have to run them all, but
But when you create a new one, it tells you what to do. It's pretty much just so it doesn't try to initially start doing like temporary files. You just add that and it lets them track it. Yeah. I accidentally added a whole bunch of temporary files. I was like, oh yes, the new dash A N, and then doing my message, so all the files. I generated a whole bunch of temporary files. Joined.
yeah, sometimes I just break it back into different and that and I and get
Go into code.
should have told me to laugh at.
Like get on my
Set up a circle with
remote origin.
I did more interesting on some shows.
Yeah.
I think
JPEG will be good more, but because it's not trusted. Did it let you pull something out?
People need to do learning about
Okay, yeah, that much.
deep learning, so that's PhD. Like, all the stuff that he talks about is exactly what we do.
It's supposed to go and build something useful.
Yeah, so like,
What are the actual
It's called naming, isn't it?
I could like building some of the stuff.
I'm really, some of this self-supervised stuff in CLR, cognition and text techniques. So it's been so much devices as well.
yes,
All sorts of
yeah.
That one, very simple in idea, with another like good.
And that's really good.
I just do
So whatever coordinates anything outside inside so wait, so when that yeah.
This one is like typically they do consistency training.
So that
One of the layers and one sort of like an input and add noise to it, or they'll take some of the layers and add noise, and then expect the output to be predicted the same. So the main innovation of this one is that they use augmentation as a noise source rather than adding Gaussian noise.
Mix up and some of the others that you do even like generating synthetic data kind of pasting. It's all these low contrast signalling.
So it's a mix of it's just generate data from solid data, like just data augmentation. Like part of this is the textual
I think they do both. You see Canvas implementation being rolled out in the last year or two. I think was it CLR that did mix up, where you cut the image out, paste it on a random background, and you expect the same either predictions or final embedding.
I'm just testing with some.
Oh yeah, Jeremy was saying the same thing. They use something for that, so that like it becomes like a 0.9 reduced to calculation.
Are we okay using the business tag?
I think that is still slightly different in that even the contrastive stuff,
This one is not directly asking it to predict when these like embeddings that are close to each other, contrastive ones, or this one is actually using the label as the contrastive element. So yeah, it's all in the same vein.
Yeah, like even I was looking for one with images to do. There's examples out there, but again, yeah, to feed it into your data loader or something like that would be quite nice, where it automatically goes and generates in the background.
Yeah. Well, you could quite easily build this into the fast.ai pipeline. They do images in the data. It's not just
Have to check it out and share that one.
yeah. Yeah, it's like
What's their background? Oh, yeah,
we could pull it up quickly.
They do this random something. This one. Yeah. And then here you go. So,
Because if you can get these results in such a small, like using these techniques.
That's the power of not necessarily needing labels, but just
Representation.
I mean, the other thing that it potentially helps with is people trying to focus on snaps. That's the way
Not so like the sort of problems you would just with basic classification.
yeah, I think it's like how Jeremy was saying, you want to have like a base case compare against. Use something like that, but we also use TF-IDF. It's quite good for if you're trying to do like keyword finding, just like statistical analysis of documents, things that the label is hard to come up with, like, or it's hard to do it nicely in an unsupervised way. You have to, how do you describe to a machine learning model, like, find me the interesting stuff? What is the labels for interesting stuff? When it's just like, it's got to be able to take an arbitrary document and say interesting stuff.
So you're saying using TF-IDF to generate labels, like it's not pseudo labeling?
Just basically that gives you candidate words that you can then improve them further with using, for instance, the data speech tags and also like look into like bigger noun phrases like that. Okay, the TF-IDF score of like the parts of this noun phrase are good, so like the things that make up this noun phrase are looking important. So it's basically more just like a traditional technique, but it's hard to replicate with anyone with more. Right.
Do you use location settings at all in your models? So for the transformer models, you can lose some positional information, but you add in an extra piece of embedding that's location.
Yeah, right. You mean like the sinusoid type thing?
Yeah. So you may find that pretty much kind of misinformation through the model.
Yeah.
all right. Does anybody need more time, or I can go through the solutions to? I'll ask if anyone actually manage to get it done first. So this first question I wrote, what changes do you need to make to chapter 10 to use sub-word tokenization, and why might you want to use it? Does anyone want to have a crack at why you might want to use it, or what changes you need to make? Does anyone know what sub-word tokenization is?
So you might be using like Chinese language characters.
Yep, that's one of the reasons you might. Yep. Yep. Yep.
And I guess it reduces the number of tokens.
Yeah, exactly. That's another good one. It's a reduction in the number of tokens that are going to be assigned to the unknown token. So for everyone who doesn't know, if you put a word into the vocab that you haven't seen before, it gets assigned to the unknown token, which basically you lose a bunch of information when that happens. So having the sub-word tokenization is if it's a word you haven't seen before, but you can make it up with two words that you have, then you can retain a lot of that information. And you can get a more efficient representation for things that end with like ly that happen all the time. That modifier can become its own piece, its own token, and then you can apply that to many things to modify them into a different form. So it helps with a model with learning those grammatical rules as well. Well, what ends up happening is that you use the same size vocab, but you fit many more words in there. So for the same size vocab, many more words will get pushed to the unknown token if you have using a word-based one, whereas if you use subword, like as you're saying, yeah, you have to have far fewer combinations to capture all the possible words, because you can any word that ends with ly or gets transformed by adding something at the end of it. So it's a word and then you change the way that it works by adding something to it. You now don't need to have two versions in the vocab. You can just have that word and its modifier, or like ing, right? If ing like doing and do, or going and go, the ing becomes one token, then you can represent all the words that end with ing in their base form and the ing. You don't need to have a separate one for go and going. Does that make sense? Yeah.
Right, so technically I could create a lot of random junk vocabulary through back translation.
There is the potential, yeah, but also that's where you can sometimes have a good indication that your model's not well enough trained if it's doing random things like that. So typically a good pre-trained language model has a good understanding of how these things fit together and will avoid making silly mistakes like that. And perhaps you need more training if it's continuing to make lots of silly mistakes. And then other things you can do is have sort of rules that you run on it afterwards to check whether things like that have happened, or to correct things like that. But yeah, I have seen that happen in real models, and it can be.
Kind of related to the question of what happens to the sequence length if you go to the model. What do you think? Like, should we increase the sequence length or decrease it?
I would increase it because it gives more context.
Yeah. So kind of more compensate for that.
Alrighty. The next thing I asked you to look at is the text generation. The reason I asked you to look at this is to try and get a bit of an understanding of how fine-tuning the language model has changed its capabilities. So what Jeremy presented was a language model that's been fine-tuned on IMDb, and the example that it spat out was, I like the movie because, I like the movie because is how it starts. And then it says, because of its stories and characters, the storyline was very strong with a very good for a sci-fi film, etc., etc. So to me, that reads quite a lot like a movie review, and it feels like it's got a good understanding of what a movie review is. So what I asked you to do was run the same thing, but without fine-tuning the model, and say some stuff about what you think the model, how it compares, basically the fine-tuning versus the non-fine-tuning. So did anyone get a chance to do that or have anything to say about it? No? Okay, well, thankfully I came with the solution prepared. Ta-da. Okay, so I like the movie because, that bit's the same. It was a perfect game. The film was featured in an episode of The Spare Man Hopkins, the other film, and other films, including The Killing Joke. And let's read the other one. I like the movie because of its rich feel and very young atmosphere. When I asked about the potential of this film, Sutherland said he wanted to use it because it's like a totally different from the rest. First I'll just ask, do you guys have any comments?
The Spare Man Hopkins is a great film.
Okay, I'll make sure to watch that. Thanks. Shannon, if you're listening at home, write that one down. Do you guys have any other thoughts about differences in the generation and what that might tell us about how well the models learn to understand movie reviews?
The sentences are more gibberish, but they're just, the grammar's all over the place.
Yeah. And the other thing, for example, this example here, when asked about the film, Sutherland said he wanted to use it because of it's totally different from the rest. What has Sutherland got to do with my opinion of the film, right? So it's writing as if it's a Wikipedia article. It's a statement of fact. Some dude called Sutherland said something about this film, and so it's not captured an understanding yet of
the original data set.
Yeah, exactly. So you can see that the fine-tuning is working when it really is learning a better representation of what movie reviews are when you compare it to yes.
Which actually raises a question I'm not quite clear on. When you talk about training the model on Wikipedia, right? And then later you refine it or fine-tune it in any code. But what knowledge is stored in that initial model? Other than constellations of words to each other, what other knowledge is there that helps going forward?
Like the grammatical rules that you were talking about?
Explicit, they're implicit in the word constellations. Right?
Yeah.
So what else is in there?
I mean, if you train on that huge corpus, actually, he knows a lot about English now. But you can see that the grammar is actually really good. He knows a lot about it.
If you're asking about is it similar to the edges in the image processing thing? Is that what you're asking?
No, I'm just trying to get it correlate the language that we are using to what is actually stored in that mathematical model, because the mathematical model at that point, if I understand correctly, it doesn't know the grammar. It knows the weights and biases and the constellation of words to each other in a certain size context.
Yeah. But like,
you can extract
which
that.
neuron in your brain knows the rule of grammar, right?
But that's what I mean. Like, I mean, we talk about that model as if it knows the grammar, but it's just a representation from which we interpret grammar, but it's not actually inherently stored there.
Well, the rules of grammar are encoded in its weights. Is another way of
And the constellation.
yeah,
And that's what's stored there,
yeah.
and nothing else.
Well, I don't know. That would be a fair assessment of what I'm saying. I think the rules of grammar are one of the things that are encoded there. The other stuff that's encoded there is a lot of factual information is going to be encoded in a Wikipedia text.
It's probably hard to know exactly what's encoded in there.
Well, you can have a look at how the word embeddings relate to each other to shows you some of its understanding. So, you know, it understands which cities are close to each other, things like that. Parts of general knowledge that you and I might know that have been written into Wikipedia. It understands the relationship between things, basically.
I wonder if part of the confusion comes in. I wonder the encoder is not just the embeddings, not just the separate words. It also includes the hidden states. So that means that it learns about the relationships between words.
Depending on the size of the context that I chose. But because we stream that into one massive long string, that is the context. And it creates correlations across the entire string. Like, remember in the very beginning of the courses, let's just concatenate everything into one big stream, and then we'll start to chop it into batches and then feed that in. So you said earlier that the inherent knowledge remains that this is a string with an ordering in it. So it actually knows that there's some form of dependency between the very first and the very last word of this.
Yeah, so the ordering
Right.
has a lot of information.
Right, yeah.
Yeah, and I think when it does something like Wikipedia, it preserves the ordering for like one document in Wikipedia. At a certain point, it's to the end of that document, and then it'll reset when it goes to the next document, I believe. Not 100% sure. The other part of that is because of the gating type mechanism with the LSTM, it's not going to remember infinitely far back. It has some context that it remembers and uses to predict, but it's not an infinite context. Theoretically, it's infinite, but in reality, it ends up not being all the way back to the very start of Wikipedia to model particular answers. It does store some information about everything, and it has a memory. It keeps information in there, and that memory is basically this constellation of weights that you were talking about. That's the set of activations is how it encodes its knowledge effectively.
So if I would take 2 pages from the if I take 2 pages from Wikipedia, one in Spanish, one in English, about the exact same topic, can that abstract the meaning out of it so that I can translate from one to the other?
Quite possibly, like the encoding will very likely contain most of the information that if you did some alignment on a decoding head. So if you have something that can already take an encoding and produce Spanish from that, and you have an encoding of a Wikipedia document in English, what you can do is there's a process by which you can align the embedding spaces, and I can't remember all the details now, but I can share a paper with you later. But then basically, once you've aligned the embedding spaces, you should be able to apply that Spanish decoding to the Wikipedia encoding of the document, the Wikitext encoding of the document, and produce a Spanish output from it, yeah. But that's the steps. You need them to be in the same embedding space, because each model, the translation model has its own embedding space of how it represents everything. Then our pre-trained Wikitext one has a different one, and yeah, there are processes by which you can align them. The reason I know about those is when you're doing, for instance, speaker recognition models, you'll train your model for a while, right? And then you put that out in production and people use it. And then after a while, more people come in. And so you have more training data. Now you want to fine tune your model. But all of a sudden, now it's producing different embeddings for the old people than what it was before. So you save their embeddings. The way you do speaker ID, basically, like you embed somebody's voice, and then you do a nearest neighbor search to a model that you've saved of embeddings of what that person sounds like, and you say, okay, yeah, these new embeddings are really close to that person, so it's the same person. Great, but now because you've continued to train your model, it's producing different outputs. So what you need to do is align those old embeddings you had and project them back into your new embedding space. And you should be able to do the same thing with your IMDb to Spanish translation thing. All right, is that it? That's the end?
Tell us more about what's under the hood of Numericalization.
Yeah, exactly. Cool. So that's that question. I thought that was kind of interesting. This one, I'm assuming since nobody ran the last one, nobody's going to run this one either. But the key takeaway from this one was we invested probably at least a day or an overnight in fine-tuning this language model. How much of a difference did it make to our final result? Was it worth doing the fine-tuning? So we got 94.3% accuracy. Whoops. I really don't like this Colab editor thing. Anyway, 94% accuracy with the fine-tuned language model. And so what did we get? It starts 83, 88, 90, 91, 92. So we've lost 2.3% accuracy. For such a large data set and so close to the 100, that's actually a massive change. So a 2% accuracy change when you have 25,000 examples in your test set is quite significant. So if you're trying to throw something together really quickly, maybe you don't need to care about that. If you're trying to get the best model out, it's probably worthwhile fine-tuning your system to get the best results. And just back to this paper, out of interest, you'll see over here, just BERT large with the 20 examples gets an 11% error rate. But after they fine-tune the BERT large on the IMD dataset, that comes down to 6.5. So they, with this BERT large, had a even greater reduction just from the fine-tuning. So that was just more like a practical day-to-day thing, like, should you bother doing this? It's better, but how much better? And so here's two examples of what sort of performance increases you can expect from going through that process.
It's interesting that the data augmentation actually gives you more performance than fine-tuning does.
Yeah, exactly. Yeah. But it's not just direct data augmentation. Yeah, it's this special way they do the data augmentation. But yeah, that is interesting. All right, so continuing on. This is the last one. Stops there. If you didn't try any of the other ones, would people like a couple more minutes to actually try this one? It's if I was going to hire somebody, this would be one of the key skills that I want somebody to have, and it's the ability to take a problem that's at a very high part of an interface to a library that you don't understand, and being able to dig into it and understand where in the library can I actually understand what this means. And if you develop this skill, it means that you're not going to have to ask your boss as often, well, how does this all work? I'm not getting it. I don't understand. So if you're new to this deep learning type tech, this is a very important skill to learn, in my opinion, about sort of like, let me say it this way. When you go into a company, your job is to make your boss more efficient, not less efficient. So make sure that you can be self-sufficient by learning how to answer your own questions as much as you possibly can. And that way you're just going to be like a superstar and everyone's going to be your best friend, because you'll get so good at it, you'll help them solve their problems they can't. So are people all interested in looking at it? I think everyone's kind of tired, but if you want, I can give you a few more minutes. Otherwise, I can just dig into how to answer this. Okay, sounds good. All right, I'll quickly go through the answer to this. Does everyone understand the question, or do I need to explain it?
Explain it.
Okay. So there's this concept of a sequence length that we learned about when we looked at batching up the language model, but it turns out when you're batching up classification samples, it works differently. So that stuff we learned before in the slides is only for the language model. When we're batching up the context, it's not the same. And what Jeremy explains is that we're going to pad all of the samples so that they have the same size in a given batch. So the way the batching works for classification samples is that it approximately sorts them based on length, then randomizes within those approximated sortings, and then chooses batches in that, and then pads them to be all the same length. So this approximate sorting means that you don't end up with one that's got 500 and one that's got 3 tokens. So you're having to put 497 pads, right? Like you're only doing ever a little bit of padding. So, and we still preserve the randomization, which is, I didn't even know about that trick. So that's a great sorter. Lots of Jeremy's stuff, when you go out into the other libraries, you'll find that he tends to put a lot of nice, neat tricks in there. So in a few years, when you've been using some other thing, do come back to look at the fast AI stuff, because there's really some good tricks in there. But then there's a bit of confusion, right? So we've got up to 500 samples in some of the things, but we've got the sequence length is 72. Like, how does that align with these big samples, and that we're going to pad them all to be the same size? So because it took quite a while to find it myself, I gave a bit of a hint of where to start looking, which is this get text classifier. And this is the thing that builds up the actual model that's used for building your text classifier. And you can see it's building this encoder, which takes in the sequence length and the architecture and what the padding is and the maximum length. So the maximum length is, I believe, the length of the longest batch size. And then by reading this, anyway, the important part is that's the encoder. And then it does a sequential RNN with the pooling linear classifier. So pooling always tells you that you're trying to reduce the dimension size. So when you hear pooling, it's about making things smaller. I'm pretty sure you guys would have covered pooling earlier in the course. But anyway, so let's go and have a look at this sentence encoder. And what I'll do is open it in a new slide, new tab, sorry. And so we see this for loop, the forward. So always PyTorch models, the bit that actually does anything is the forward. That's what's going to get called when this module is used. And we see, interestingly, there's this for loop here, which goes from 0 up to SL. So the input batch comes in, we've got batch size by SL. So that's telling us that this SL is representing the padded length of that batch. So however big it was, let's say the longest one was 500, all the other ones got padded up to 500, and SL represents that 500. So that's very interesting. That's one of the parameters we're interested in. And then we see this SL is used in the for loop, where the outs, these O's, get created by running self.module. Module is the architecture that got passed in over here. So we see here, Arch is the architecture. So that's going to be the LSTM, AWD, LSTM, or transformer, or whatever special thing is going to produce some encoding O for this input, and we see that it's doing that in a loop and building up these O's with appends as it goes through the loop, and each time it's taking steps of size self dot back propagation through time. That's what BPTT stands for. And how was BPTT defined? It was the first element in this class. So let's have a look what that was. That's the sequence length. So the 72 is telling us that this for loop is taking slices of size 72 through this overall batch of size SL, and appending those encoded outputs to the outs matrix, which then gets concatenated together. That gets returned and then fed into the pooling linear classifier. So I know that that's quite a lot, but a useful skill to develop over time. And I would encourage you, when you get stuck, the first thing to do is to try and do this yourself. Try and get lost, even if it doesn't work. And then when you go to help with somebody, be like, what I did was I followed it down into the code to here, but I just can't understand it, I can't find it. And they're going to be more willing to help you because you've demonstrated that you're willing to go the extra effort to understand it yourself before coming straight to them. So I hope that was useful. Does that make sense? Does anyone have any questions? No? All right, that's all I've got today. And I think Michael's going to say some additional things.
Thanks so much, Jaco. Amazing, really good. All right, so I haven't actually got any slides prepared for you guys, so I'm going to go through a little bit about what the plan for the rest of the course is. So tonight's obviously the last actual lesson of the Fast AI course. So from here on in, we've basically got one more week of Tuesday nights, so in 1 week's time, and then we've got a final sort of showcase, which is when the judging is going to occur. So basically, let's walk forward over the next couple of weeks of what that looks like. So tonight's the last week of learning. Basically, it means from now on, all you guys really need to work on is your projects. So next week, because there's no lesson, what we'll probably do is maybe a presentation or two of, adjacent topics that you guys are going to be interested in. We've talked about those before. So things like, how to get your first job in the industry, or the sort of skills that you guys should be looking at next. So us as the mentors will look to prepare that over the next week. Other than that, though, as far as homework for you guys, it's really just your projects. So basically, over the next week, you guys should all be working on those projects. Hopefully, your modeling pipelines and things like that are all fairly tidy by now. Basically, next week I'm thinking Tuesday, maybe we make it the next day, just in case we have some sort of, people who need to make some changes. But basically, you need to have that ready to go, sort of put together, and basically a submission to submit to us as mentors. So rather than everyone presenting that up on stage, what we're going to do is ask all of you, because there's a lot of people, to basically create either a little video recording or a voice recording, basically a summary of what your project is, the same sort of thing that you'd present if you guys get picked as one of the top teams to present to the judges. It doesn't necessarily have to be a video or super polished if you don't have all the time to prepare, but it should give us all the information we need to understand, right, what have you guys done? How did you build it? What are some of the techniques you used? What problem are you solving, and what are the results? So
Yeah, that's going to be a week from today. We'll probably try and cap it at like 3 or 4 minutes so we can get through them fairly quickly. And then basically what we'll do is the mentoring team, we're going to go through all of those submissions, each give some scores, and then we'll basically just average those scores from all the mentors and pick the top teams. We'll probably select 6 to then go through and present at the following Thursday at the Queensland AI meetup. So the way that we're going to score that, we'll need to finalize exactly what the criteria is, but it's probably going to be things like creativity, both in the problem that you've looked to solve and also the way that you've tried to solve it using machine learning. Usefulness, or like what's the actual application of what you're trying to build? Is it something that has utility or is useful? The technical approach and execution. So what's the approach that you've used? How not necessarily complicated. It should work fairly cleanly, but are using more advanced methods, and when you've gone and done them, have you executed them well? Next one will be probably around difficulty, so that teams who have focused on more challenging problems and more challenging modeling approaches, will probably get a bit of an advantage there because it's going to be a little bit more difficult. And then I'm thinking the final one is probably actually about your presentation itself. And that should be, it's probably actually more than 20% of the total score. But you guys should be able, you spend a lot of time on the code. When you actually present this, that's the most important piece of the puzzle, making sure that you can communicate what's the problem that you've solved. For anyone who hasn't seen it before, it's really clear what you've done. Here's how we went about it, and here's what it means. So that'll probably be the last one, and obviously a really important part of it, particularly if you do end up going through to present to the judges. So we'll basically go through all of those, as many mentors as we can sort of get through, as many as we can, or rather, we'll all try and get through all of them, and hopefully we'll have many mentors who can. And basically we'll then select the top 6 teams. And those top 6 teams then need to basically polish up their presentation. You'll have a little bit more time if you do want to sort of improve on your pipeline. But basically get that ready so that you can present that either in person or via Zoom to our panel of judges the following Thursday. So just to sort of map out again, that you'll need to submit in 1 week's time your presentation, something digital that us as the mentors can consume. Within 2 or 3 days, we'll judge as many as we can, or as many of us will judge, and basically we'll come up with a list of those who get through to the sort of final. And then 1 week after that, on Thursday the 5th of August, our top 6 teams will present at the Queensland AI meetup to our panel of judges. So who is our panel of judges? So our panel of judges, at this stage, we have 2 out of 3 locked in. The first one will be Jeremy Howard. Obviously you know who he is, so he's going to be involved. We're going to have Sue Key, who is the CEO of the Queensland AI Hub. Queensland AI Hub have obviously been really helpful in helping do a lot of the logistics behind the course. And then we're also looking to get someone from AWS, because they've been so kind to give us this space and sponsor the course. So I'm just waiting for them to lock in whoever that will be. But it'll be someone who's familiar with AI and maybe looks at things from less of the technical route, more of the solution and stuff like that. So we want to have a bit of balance between pure technical and what you guys present. Yes, good question. So I would highly suggest that it uses fast AI. However, I think the one example where it's possible that you may not want to use fast AI, or it may not make sense, is that there's some things that fast AI can't do, or where it makes more sense to use something else. So I think you're going to have a good reason why you didn't use fast AI, because at the end of the day, I think fast AI is a really good toolkit. That's why we're all here, and obviously we want to show that you've built something from what you've learned in the course. But again, it is about what you've learned in the course. So if you've started a problem with fast AI, realized, actually there's another library that maybe has some bells and whistles that makes this problem work a bit better, and then you switch to that halfway through, I think that makes sense. It's going to be up to you guys to sell that. So obviously you want to use fast AI, but if you can convince us there's a good reason why you couldn't do it and show us the why, then, you know, I think that makes sense. So that's my view. But again, this will come down to the judging panel with, you know, making sense, is this the right way to solve the problem? A couple other notes on your presentations. Don't just present a slide deck that has, you know, limited information. It says, here's my accuracy score, and voila, that's great. You know, it's not just about getting a number on a screen. It's about presenting a solution to a problem. So make sure that it's, you know, the only time that just having a score is going to be good is if it's a new state-of-the-art result, which I don't think anyone will have new state-of-the-art results in the short amount of time we've had. So please make sure it's a bit more engaging and there's a bit more about the problem and what you've used to solve it. Try and make it interactive. If you have time to build a little web app that, you know, spins the model up, has a little front-end UI where you can upload an image or type in some text and it sends a result back, like, you should all be aiming for that. Really, really suggest that. That's probably going to make the difference between the top teams and those teams that don't make it through to the final. Try to make it entertaining, you know, both in your presentation style and also the problem you're solving. You know, make it cheeky or whatever. You know, use real data to feed the model and get predictions. You know, this is up to you guys to figure out what that means for your projects. Make sure that you submit at least some of your code. You may not want to submit all of it, but you know, in order for us to make an assessment of how fitting your solution is or how well you've executed on your idea, we need to see some code. So you'll need to share, you know, at least, you know, your model training and your model training and maybe your transformation code for the data. If you don't want to share your Django app that you've thrown together after some Code Academy lessons, then sure, but at least your modeling code you should want to share. And yeah, the last thing I had down was strongly suggesting using fast AI. We've been through that. Any questions? And online? I don't see any. And I will put this together in a PowerPoint and share this afterwards in the channel so that everyone, both in person and online, can get this and get the dates. Cool. So yeah, the dates that you guys should be thinking about is 1 week time. You want to have everything polished up and in either do a screen recording, walking through it, have an accompanying slide deck, something like that. I might flesh this out a little bit more, give you guys some ideas of what that might look like. We'll then, you know, select the top ones and then you want to be free the following Thursday. That meetup, I haven't put it up yet. I confirmed with Jeremy today that we have at least 2 of the 3 judges. I'll get that up in the next 24 hours and I won't send emails out to the whole Brisbane community. So you guys are going to get probably only 24 hours to RSVP to that if you want to make it in person, because that will fill out within 2 or 3 days. So I'll put an announcement in the channel, but yeah, if you do want to come in person to that, you'll need to RSVP once it goes up. Cool, and that's pretty much everything as far as the projects go. Yeah. Oh, the only other thing will be that also working with AWS to get some prizes for the sort of winning teams. So yeah. Cool. Any questions, guys? All right. Awesome. I'll get a deck together and put it in Discord with some dates. You guys have some deadlines to work to, and yeah, we will see you next week. Awesome. All right, guys. Have a good week. Chat soon.